Welcome for our science lesson. In the previous lesson we were learning about the geological period, and we learned various errors that have been come up with the scientific innovation. Nowadays we are able to estimate the number of age the planet Earth and other substances have lived or have been in existence. Just to make a review over the last bit of the lesson, we have to respond on this few number of questions before we move to the next question. My first questions asks us that you have to state how scientists believe the Earth to be. State how scientists believe the Earth to be. My second question asks us that we have to list the following errors in order. We have to list the following errors, that is in order, starting from the most recent. And then those errors are Paleozoic, Archaeozoic, Paleozoic, we have Archaeozoic, Archaeozoic, and then we have Azoic, we also have Proterozoic and Mesozoic. Those are the errors we have been given. We have to list them in the order. Then list down 3 periods that make up the Mesozoic era. That is question number 3. We have to list the period that makes up the Mesozoic era. Mesozoic era. And then question number 3 or question number 4 ask us to define the term fossil. Question 5 asks us to identify what uranium, or identify how trees can be used to trace back. We have to identify how trees can be used to trace back through time. Identify how trees can be used to trace back time. And then the 6th question, which will almost be the last, we also have to identify we have to identify what uranium changes into. What uranium changes into over a period of time. Over time. And our last question will be identify an example of an index fossil. Of the index fossil. We have to identify an example of index fossils. Those are the 7 questions that will help us to review our part on geological period. Then as we move on, we shall be able to look at the radioactivity. Okay. State how scientists believe the Earth to be. They are trying to ask the existence of the Earth, the age by which scientists have come up with. And we have to remember that because of the geological period and the various methods that have been used to identify the era or the existence or how old the Earth is, scientists have estimated that is an age of between 4.5 to 4.7, that is billion years old. This is what the scientists believe the Earth is old. List the following era in order, starting from the most recent one. We have the Paleozoic, Archeozoic, Azoic, Proterozoic, and Mesozoic era. When we come to identify them, to list them in the order, starting from the recent one, when we look at this one, first of all, we have to begin with the Mesozoic era, because that looks like the most recent. We have Mesozoic era, and then from that is the major one, and then after the main Mesozoic era, we'll have to go after Mesozoic era. We have is Paleozoic. We have Paleozoic. That is Paleozoic era. That is now in the order, starting from the most recent. Remember, we have the Conzoic era, and then we have Mesozoic, and then Paleozoic. And then the rest that are remaining, we have looked at the Paleozoic and Mesozoic era. The remaining fall under the Precambrian. And under Precambrian, we'll have them listed down as the Proterozoic, we have the Proterozoic era, that is begin with Precambrian, and then we have the Archeozoic era, and then lastly we have the Azoic era. Azoic, these are found in Precambrian. These are the ages that are found in the Precambrian, which is almost the last age in the geological order. Therefore, starting from the recent one, we have the Mesozoic, and then we go to the Paleozoic, and then followed by the Proterozoic, and then Archeozoic, and then the last 2 age is the Azoic era. These are the eras looking at their order of reasons. Then we have to list down the period that makes up Mesozoic era. While we were looking at our chart, actually the Mesozoic era is made up of 2 periods. And one of the period is Jurassic period. It is called Jurassic period. We have Jurassic, and then the second period is Triassic. The Triassic period. Therefore, there are 2 periods that makes up Mesozoic era. And then they are also asking, that is question 4. Define the term fossils. What is a fossil? We learned that a fossil is a remain of a once living organisms that died and they were buried. They were buried in the soil. That is the meaning of the term fossils. Identify how trees can be used to trace back the time. Actually, when we go and look at the trees, we study the growth ring. By studying the growth ring, I hope you are able to remember that one. When we study the growth ring, then we are able to find out, we can be able to trace back how trees can be used to trace back the time. That is the ancient time. Question 6. Identify what uranium changes into over a period of time. Try to answer that one. Perhaps you will remember quickly, uranium over a period of time, it changes into lead. When we bring it under radiometric dating, we'll find that it changes into lead. This is the lead, or we can also use the chemical symbol. The last question, identify an example of an index fossil. An example of an index fossil. Index fossil, remember, we learned that they are fossils that are short-lived, they have been formed and for a short period of time, and therefore mostly they are found on the edges of rocks. An example is the ammonite. Ammonite is an example of the index fossils. Looking at this, we are now able to understand the concept of the geological period, where we have been able to look at the Conzoic, having 2 periods of Quaternary and the Tertiary, and then Mesozoic has 2 periods also, that is Jurassic and Cretaceous, and then Paleozoic has various, that is around 6, that is Permian period, Carboniferous period, Devonian period, Silurian period, and Ordovician period. While we also look at the Cambrian period, that is the last bit, and then the Precambrian period itself is also divided into 3, and we'll be able to look at it at the next level. Now, at this time, we are going to look at radioactivity, fare a little bit in details. We will look at it fairly in details so that we identify how it is happening. We identify how it is happening, and that will help us. Radioactivity. Radioactivity is also known as nuclear decay. Radioactivity is also known as nuclear decay, and radioactivity is actually the process by which unstable atomic nuclear or nucleus loses energy in terms of masses. And it does this by emitting radiations. That process happens by itself emitting the radiations, and there are three types of radiation that are always emitted. In the previous part, we looked at the radiations that are emitted. The first one is the alpha particle. The second one, we have the beta particles or the beta particles, or the beta particle is all emitted during the radiation. And then lastly is the gamma particle. Looking at this process of radioactivity, which leads to unstable atomic nucleus losing energy in terms of masses, we'll be able to look at various radiations that are emitted in. And in the process of radiations, the alpha particles are emitted, the beta particles are emitted, and also gamma. This gives us the three types of radiation. We have the beta particle, which is emitted during the radiation, and then alpha particle, which is also emitted, and then lastly the gamma particle. And then when we bring it or we translate it in radioactive decay, the alpha particle is denoted as, in chemical, as A, the first letter, and then the beta particles is given as this denotation, this is the unit, and then the gamma particle is given as this. Therefore, mostly in ancient, the scientists used the first letters of Greeks which were appearing. Therefore, alpha is denoted as this, or sometimes they denote it this way. This also can be a denoted of the alpha particle, just picked by the first letter of the Greek, and then we have the beta particle and then the gamma particle. When we bring them in the reactivity or radioactive decay, they will undergo, the alpha particle will undergo what we call the alpha decay, while beta particle will undergo what we call the beta decay. And then gamma particle will take a notion of gamma decay. Those are the various processes of decaying, and we are able to learn that any material that contains such unstable nuclei is considered as a radioactive. Although some are short-lived nuclei, which states can decay through neutron emissions or even proton emission, especially the short-lived nuclear states can decay through neutron emission. We also have the proton emission and so forth. Therefore, we learn that the radioactive decay is actually random. It happens in a random manner. We'll be able to look at them. The radioactive decay happen in a random manner. That is, when it happens in a random way, scientifically they say it happened in a stochastic order or stochastic manner, that is according to the process of the level of the single atoms they have. And that is basing on a scientist who came up with the quantum theory. We'll be able to look at it in the at the higher level. And actually, this random state of the radioactive decay, when it happens, it is the one that forms the basis of radiometric dating. Radioactivity, when it happens in a random manner, it leads to the formation of the basis of the radiometric dating, where we were able to identify two methods. One is the absolute dating, and then another one is the relative dating. Therefore, when we look at the absolute dating, this is where the expected decay rate is actually characterized by the measure of the decay constant. And the measure of the decay constant, we were able to recall and refer to it is a half-life. Therefore, any radioactive atom has actually has no upper limit that ranges. Any radioactive atom, you should be able to understand this one. Any radioactive atom, all the radioactive atoms have an upper range of over 55, have an upper range of over 55 order of magnitude. And this magnitude is very high. When we take it to the radiometric scale of the radioactive atoms, in a ranging scale of 55, it is a higher order magnitude. Sometime when we are able to explore this, the higher order of magnitude, it happens from nearly instantaneous for longer age than even we are able to determine the age of the universe. Because it takes longer age than the earth itself. Therefore, when we subject our radioactive atoms, various types of radiations that are emitted, and then because we will have the radiometric range having an upper range, because it has no limit, it goes up to 55. That is the order of magnitude which has been taken to be to have a longer age than even the age of the universe. That means we are able geologically to determine the age beyond and even before the existence of the earth using the radioactivity series, when we are able to study the radioactive elements. From nearly there, we will be able to explore various elements over which the alpha decay is taking place. Let's look at the alpha decay. When we look at the alpha decay, it is a type of radiation. It's a type of radiation that gives out the radioactive decay in which the atomic nucleus emits. Actually, when we look at it, it emits an alpha particle, and thereby this alpha particle is broken into an atom. That always this atom has a mass number that has been decreased by 4. This atom, when it releases an alpha particle which changes into an atom. This atom will always have a decrease because it has decayed. It decreases the mass number. The mass number has decreased. The mass number has decreased by 4, and then the atomic number we have the atomic number also decreased by 2. That is decreased by 2. Therefore, for example, the mass number of sodium is 32 and 22. This is the mass number and this is the atomic number. When it reduces by 2, it will form a new atom, and that we subtract 4 here, we will have, that is 28. And then reducing by 2 becomes 20. Therefore, we will have a new atom. Therefore, it has decreased. And this is what we have to say that it has undergone the decay. And during the process of the alpha decay, we call it alpha decay, the atomic nucleus always emits an alpha particle, and thereby it decays into an atom that has a mass number has always decreased by 4, and the atomic number decreases because it's very large. And sometimes, because it has a large mass number, up to 7,000 times that mass of a beta particle. From the previous example, when we look at this reactivity, we'll be able to review our questions and find out how does it happen. Let's also move to the next part. That is the beta decay or beta radioactive decay. When we come to the beta decay, the particles are high energy and they always have a high speed of electron for certain type of radioactive nuclei, such as the potassium 40. For example, when we look at the potassium 40, potassium 40 is a very reactive element, and when we look, it has a high, the energy moves at a very high speed, and also the electrons moves at a high speed. The beta particle here have a greater range of penetration than that of alpha, but still they are much lesser than the gamma rays. They have a high or a greater penetration range compared to the gamma ray and also the beta particle. For example, when we bring them to the scale, when we bring them to the scale, and then during the radioactive decay, you will find that it is the beta particle that is always has a high penetration. It penetrates through this object and find it on the other side, while at the same point the alpha particle does not have to penetrate. And then we'll also, when we look at the gamma ray, its penetration level is very low. That is why it forms various level of penetration to a given object. And that is why we will say the beta particle have a high penetration, because, for example, the potassium 40 has a high speed moving electrons that makes it to have a high penetration power than the alpha particle and also the gamma particles. That is just to give us an example of the scale of how the beta decay occurs. To give an extent, when we look at the gamma decay, the gamma decay involves electromagnetic radiation, which now these one are more stronger because of very high frequency, and therefore they have a high level of protons. They are always produced by the decay of the nuclei as a transition from high to low state. Most of their reactions are always accompanied by the gamma emissions. When we look at the various worked examples, then we'll be able to understand. Let's go back on our index notation. Then we find out how it happens. That's now the radioactivity itself in its half-life. This is an example of an alpha decay happening. Okay, the previous example I gave you, I picked it from the same. Therefore, there is no much doubt when we relook at it. How many years will it take? How many years will it take? That is 88 grams of tritium. How many years will it take for 88 grams of tritium to reduce into 11.0 grams, given that a half-life of tritium is 12.3 years? From the previous solution, we were able to find out that we have to take the mass that is reducing, and then we have to divide it. That is 11.0 grams. When we divide by 88 grams, this one will give us in which it gives us, that is the third category, that is 0.125. And then we bring out our formula of a half-life. Is given by this. This is the formula. And then we equate it to 0.125. Therefore, we want to get how many years will it take. We have now to introduce the log, that is log 0.5. This is a half is 0.5. We equate it to 0, that is log. We also have to take the log of 0.125. Then we have to find the number of n, that is by dividing, that is log 0.125 divided by 0.5. Then our n will always be equal to 3 if we worked it out. Our n will be worked it out that way. Then we are finding out how many years will it take. If they have given us a hint of tritium taking, that is 12.3 years, to reduce into this, and then it is in the category of, that is the 0.125. That means we have to take, that is 12.3, we multiply it by 3, and then we will get, that is 36.9 years. That is a half-life. Therefore, when we have to bear this one in mind, always this one is 0.5. And then in the second is 0.25. If it is 2, 0.25. And then if it is a half-life of the third level, it is 0.125. When we move, that is the fifth step, the fourth step. The fourth step is 0.0625. As we go, it reduces. Therefore, this is the logic that we are using. Because in 3 years, we'll be able to find, we have to divide it by a third, which is equal to 0.125. This is, we are dividing by a fourth, and then coming to it, we have to reduce from 1. Therefore, as a half-life goes and reduces, we are able to find out that there are various changes that are taking place. Let's look for another example. Let's look at another example of this radioactive decay determining the half-life of given substances. How many years will it take 100 grams of an isotope for 100 grams of an isotope to reduce to 12.5 grams of an isotope to reduce to, that is 12.5 grams. That is an example 2. We have to look at it. so that we are able to learn the radioactivity series. This one will have to determine, it's very simple. How many years will it take? When we have to take 100 grams, and then we divide by 12 grams, that is 12.5 grams. It will be able to give us directly the period. We can also use this as another way. When we take 100.0 grams, divide by 12.05 grams, it will take us, very simple, we take 100 and then we divide by 12.5 grams, we'll have to get, there are 8 years. And always when we find it, this one, when we look at the number of years it has taken, it is 8 years. But in which level is it found? It is found in the 3rd level. It has gone up to the 4th, the 3rd steps. And simply, we can also look at it as the same to find out if it is right. Suppose here we have found it is at 8. And then it gives us an equivalent of 0.125. What we are going to do is to have 8 log 0.5. We equate it with this. That is log 0.125. And then we take the division, that is log 0.125. We divide by 0.5. We'll find that. Let's try and find out if it will give us the same. We are going to get, that is 8, going to give us, that is 0.25. When we bring it to 0.25, it is in the second. It has taken 2 steps. Therefore, a half of 8 years is simply 2 years. It will take. And that brings us to that understanding that when we look at the reactivity series, we are able to find out the period over which a given mass can reduce. Having looked at this, there is also another simple way of looking at it. If a half-life of 100 grams of an isotope is 8 years, if 100 grams of an isotope is 8 years, how many grams will remain in 32 years? How many grams will remain in 32 years. Simply, we have been given two periods here. We have a period of 8 and also 32 years. Therefore, they are asking us the reduction, their half-life of a given isotope that had 8 years or has brought up to 8 years, and how many grams will it remain if it continues to take 32 years. The solution to this one will be able to find it differently in this way. This is now another different way. We have to take 32 years and then we divide by 8 years. Simply we will get 4. When we look at these questions, it requires us to look for how many grams will remain in 32 years. And solution, simply we look at 32 years, we divide by 8 years. There are a series of 4 steps it will undergo for this isotope to make a complete decay. Therefore, the grams that we are going to look at is after a period of 32 years. Therefore, in a period, we take as it is original, that is the parent to the daughter and the subsequent daughters. We take 100, a half-life of 100, that is step 1, it gives us 50 grams. And then we take as 50 grams as the second step, a half-life of 50 in the second step, it becomes 25 grams. And after giving us 25 grams, we subject to the third step, it will give us 12 grams. And lastly, the fourth steps will give us a half-life of 12.5 is 6.25 grams. Now, we can make some various comparison here as we take a half-life. We have been able to find out Therefore, when we take the comparison of 4 here, the 4 steps will give us, that is 0.0625. And then we will get, that is 4 log 5, 0.5, gives us 0, it gives us log 0.0625. And then we get 4, and then we divide by the log, that is 0.0625, divide by 0.5. It's going to give us, that is 25, when we divide in the subsequent. It brings us, that is to 0.125. And as we look at it carefully, we have 4 years, 0.0235, or 0.125. It has given us 4 years. And it has given us the grams of 6.25. Therefore, we'll have to take 3. This one is in the third category. We multiplied by 4, not 4 actually. This one 0.25. It is found in the third category, that is, we have to divide it by 4. Therefore, it becomes, that is 4 multiplied by initially 8, it will give us 32 years. Therefore, the same has proven us. How long will it take? You will have to take, this is 4, which is our initial stages, 4 steps that has undergone, has taken the isotope 8 years and then bringing us to 4 years. And then after 32 years, the mass that will be produced or that will remain is 6.25 grams of that given isotope. And this makes us to be able to understand various radioactivity and how it has happened. We have been able to look at the types of decay. We have been looking at the reactivity, that is radioactivity, and there are various types of decay. I will just give us this question for us to discuss. You list down 3 types of radiation and state their radioactive decay. Therefore, this is our question to summarize the whole part of this topic of radioactivity under the Earth's fragile crust. We have been able to look at various concepts of geological period and the radioactivity. Having looked at all these, we'll be able to short, just simply you have to list down 3 types of radiations. There are actually 3 types of radiation, and these radiations will in turn give out the radioactive decay. You'll have now to state the radioactive decay, as you have listed down the types of radiation. And here to help us, the one type of radiation is the alpha radiation, which gives us an alpha particle. And then the second one gives us the beta particle, that is from beta radiation. And then the third one that is listing down, the third one is the gamma particle. The gamma particle. These are the types of radiation, or we can just call alpha radiation, beta radiation, and also it can also be called the gamma radiation. And then listing down or stating down their decay, the alpha decay, their radioactive decay of alpha will be called, that is alpha decay. Alpha radioactive decay. And then this becomes beta radioactive decay. And then lastly we have the gamma radioactive decay. We have already answered our questions appropriately. Therefore, having this in mind, we are able to look at various concepts on radioactivity that will give us 3 types of radiation. That is the alpha radiation, beta radiation, and then gamma radiation, which always emits the alpha particle, beta particle, and then the gamma particle. Therefore, in the radioactive decay, the alpha particle will produce what we call the alpha radioactive decay, and then the beta radioactive decay, and then the gamma radioactive decay. Coming to understand that, we have come to an end of this concept. We shall meet in the next lesson as we look for further concepts. Thank you.